All right. Hello, everybody. Okay, so as promised in class, I'm now going to work through problems 5 through 8 on the exam 3 that you all took just before Thanksgiving. Okay, so let f be continuous, and recall that e sub n of x is what it usually is, and let g sub n of x be blah, that thing. Use the definition of convolution to prove that g sub n convolution f of x is equal to, well, that sum on the right-hand side. And so this is meant to be a computation. So by definition, so it starts with the definition. So the definition of convolution is that this is equal to the integral from 0 to 1 of g sub n of x. G sub n of x minus t. That's right. So the whole point is that, oh my goodness, do I even remember the definition of convolution? There we go. Right. So it's a function in x that's equal to the result of an integral taken in t. And the way to remember what goes into those arguments is that the sum of those two things, that sum is equal to x. Because what you're actually kind of adding up is the number of, you're sort of adding up the number of ways to take two elements, or 0 to 1, mod 1, and add them up and get x. So there we go. Okay, so that's the definition of convolution, which I thankfully remembered just in time. So the integral from 0 to 1 of, what's g sub n of x? It's the sum as k goes from 0 to capital N of e sub 2k of x minus t. F of t dt. Now, by the sort of usual properties of the integral, you can pull out a finite sum. It is just a finite sum out of an integral, because the integral of the sum is the sum of the integrals. And so we're left over here is e sub, how much space do I have left here? Okay. I'll go ahead and make this take 2 steps. So I can pull out this sum over here. There we go. And so let me remind you that that in the usual way, e sub n of a sum, if you sort of write out the exponential involved by the usual properties of the exponent, which we so painstakingly proved actually work, e sub n of a sum is equal to the product of the e sub n's. And so get the sum as k goes from 0 to capital N of 0 to 1 of e sub 2k of x times e sub 2k of minus t f of t dt. And now, because the e sub 2k of x is a constant with respect to the integral, the variable integration, which is t, you can pull out that e sub 2k of x. And we're left with the integral of 0 to 1. I'm going to have the f of t in the front, reasons that you probably realize, but just in case, let me remind you that e sub 2k of minus t is e sub 2k of t bar. This is all, I hope this is all kind of familiar from the homework. And the reason we did that is because that's the definition of, well, that is exactly f hat of 2k. That's the definition of the Fourier coefficients. It's the sum as k, the 2kth Fourier coefficients. The sum is k goes from 0 to n of e sub 2k of x, f hat of 2k. And is that, yeah, that was what, that's what we wanted. Yay, yay us. Good going, us. Okay, so there's problem 5. Any questions so far? Oh, when we pull, when you pull out a finite sum from the integral, that's the property. That's just the properties of the integral. The continuity thing that I'll show you where the continuity thing shows up. It's only required for infinite sums, and it's not the continuity of the integral so much as the continuity. Well, it's the continuity of the integral as a function on L2 on L2 space on L2 of S1. It's like function space continuity and not like like regular function continuity. A good question. Yeah. So we don't. This is just. This is not any kind of continuity thing. It's just property. It's just the integral of the sum is the sum of the integral. This is just properties of integration. Okay. Any other quick questions? All right, I mean to hustle you along, but my computer, I just don't know. Okay, so that's that. I said that's that. There we go. All right, so this is like negative advertising against Dell computers. This thing is so terrible. Okay, so soon enough I'll buy a new laptop. All right, define this as a limit of finite sums, and so okay, so the first is that the first thing, and this kind of gets to your question. So how do you define an infinite series as a limit of finite sums? Well, the finite sums are the partial sums of the series, and so f is the limit as capital N goes to infinity of the sum as n goes from little n goes from 1 to capital N of Cn un. So that's the definition of an infinite sum as a limit of finite sums. And so now you want to prove that for oh yeah, that's right. There's no integrals here. Yeah, well, maybe that's okay. Maybe I didn't fuss with that too much, but yeah. So there's no integrals here, by the way. So there's no just so. Gosh, I should have been maybe more fussy about people. Well, okay, I'm not gonna take anybody's points back now, but if anybody wrote down integrals, well, there's no integral here. So it's just an inner product space. And so kind of the only thing you can do here. Well, it's not the only thing. Actually, it's not the only thing because there is some there was at least one person who had a really interesting alternative solution to this, just like totally different methods. Okay, but anyway, so I hope, based on what we've done in homework before, the thing to do, the sort of way to tackle this expression, the inner product of f and uk, is to plug in that infinite series definition of f and sort of start going to town on this thing. Okay, so that's just plugging in part A basically. Okay, and now here, yeah. So each time you pull out a limit or an infinite sum, here is where the continuity business comes in. I'll try to be precise about this if I can ever get the color change thing to show up. There we go. Okay, so now, yes, here we want to pull out the limit. capital N, CNUN, UK. So I think if you just said that you can pull out an infinite sum because of the continuity of the inner product in the first variable. I think I would have probably let that go, but just to be careful about it. So anyways, the point is that the reason that you can pull out limits out of an inner product is because inner products are continuous, is that the inner product is continuous in the first in each variable. I mean, I guess you could have done it in the second variable too. All right, so that is sort of that's the big place where continuity is used, and so that it's always sort of in the end it's always some variation of continuity. By definition means you can sort of pull a limit out of a function. That's the sequential definition of continuity. So, does that make sense? That distinction? Yeah. Okay. Yes, that's right. We proved that in homework that yeah. Well, basically that the inner product is continuous in each variable. Okay. For the rest, excuse me. So this is the limit. So this is going to stick around outside. And now this next bit is just a finite sum. So this next bit is just comes from properties of the inner product. And in fact, the step after that comes from properties of the inner product. And I think, actually, I think I'll feel better so that's really just the definition of inner product. You didn't have to write that, but if you're wondering where those steps come from, that's what's happening there. And what I'm going to do now is I'm actually going to reconstruct the infinite sum outside here, leaving the Cn alone for the moment. And now it sort of makes the next part of the explanation a little cleaner. Okay, so now what happens is in this next step, it's going to be because we're given that we're given that if n is not equal to k, then un, the inner product of un and uk, is 0. Right, because it's an orthogonal set. That's the definition of orthogonal set. Oops. Whoa, come back. Orthogonality. And so what that means is that the only term that in that infinite sum that survives is when n equals k. So this is ck, the inner product of uk and uk, which I hope is what we're supposed to prove this is equal. Well, I mean, this is what it's equal to. Yeah, there we go. Well, that's what it's equal to. Hopefully, that's what I ask you to do. So yeah, as advertised. Okay, there's a nice fat smiley face. Okay, so questions. Okay, so next. All right. Oh, this is so. I hope you can tell that this is like a kind of really complicated way of just saying like, well, do the estimate that you did in the homework. Um, all right, but okay. So this. So let's see. So we're given that the integral from -1/2 to +1/2 of absolute value of f is 3, just because, and let h be a real valued function in two variables, x and t, such that h of xt is continuous in each variable, holding the other one constant. And actually, I realized as I was grading this, I should have realized that, this is what I get. This is what you get when you make something fresh, right? Like when you have like fresh baked goods and they're homemade, sometimes they look a little funny and there's like extra parts or, parts missing. So this is really just saying that h is continuous at 0. It is independent. Okay, it's not entirely redundant. And that continuity is like uniform in the variable t. So it's independent of t. I guess you need to know that. Well, okay, so that wasn't completely ridiculous. It wasn't completely redundant. So now let G be blah. So prove for every epsilon greater than 0, there exists. And so, I hope one thing that a muscle that you've built in this class that you can sort of, in retrospect, apply to 131A is that you say like, aha, for every epsilon greater than 0, that means I should pick. We assume there's an epsilon, and there exists some delta greater than 0. So I'm going to let delta be something. Such that if assume the absolute value of x is less than delta, then, oh my gosh, have I even left enough space? Then the conclusion all the way down here is going to be that the absolute value of g of x minus g of 0 is strictly less than epsilon. Okay, so so that's where, well, okay, I'll pull out for this. Yep. So there it is. There's the sort of big picture outline. And so I hope you sort of have by now built that this muscle that says like, oh, if I'm gonna do this epsilon delta business, well, I better this is I can let somebody else pick an epsilon. I'm going to pick a delta in response. I'm going to look at some x with the absolute value of x is less than delta, and then God willing, at the end we get the g of x minus g of 0 is less than epsilon. Okay, so that's a great muscle to build. So for the final, you have to do something like this. Maybe an epsilon n, maybe an epsilon delta, maybe both. So that's a good thing to actually. So this is not a bad time to pause and ask if there are any questions so far. Okay, so now let me make one comment here. Here's something one thing you should not do. One thing you should not do at this point is that, well, okay, one thing you should sort of be ready to do, I guess, which is that it seems highly unlikely that there's going to be a formula for delta in terms of epsilon, like a precise formula, because what's happening here is you're proving some sort of continuity-ish or limit-ish kind of thing that's sort of based on a previous continuity-ish or limit-ish kind of thing. And so yeah, I mean, if you had, so without further, I mean, I guess I wrote the problem, so I know what's happening next. But if you didn't have any further knowledge of the problem, you're just doing this, and you say like, well, whatever you're writing here, probably it's not going to be delta equals like 5 epsilon or even 5 over epsilon, because there's too many things that you know nothing about here, right? There's you don't get like 5 over epsilon unless you actually sort of really know something strongly about the sort of setup, the functions in the setup. So And in fact, there's this delta 1 over here that's kind of come into use here. So I think it's pretty reasonable to think that whatever delta is going to be delta 1 of something. And we'll fill that in later. But it's going to be delta 1 of something else. Okay, so that's 1. So 2 is, well, our goal, right? If you're driving from San Jose to Los Angeles, I can't resist saying this again. If you're driving from San Jose to Los Angeles, what do you think about? You think about Los Angeles. So Los Angeles is g of x minus g of 0, or the absolute value thereof. So which means it's pretty reasonable to start by looking at the absolute value of g. Oops, actually, move this over. The absolute value of g of x minus g of 0, which is equal to, oh goodness, the integral from minus 1/2 plus 1/2 of h of x t times f of t dt minus integral from minus 1/2 plus 1/2 of h of 0 comma t f of t dt. That's and absolute values of all that stuff. And so, as we have done in many homework problems, there you now want to combine the integrals, and the integral of the sum is the sum of the integrals, and so we get this. Parens h of x of t minus h of 0t times f of t dt. And now, to make this work out, well, how do you always estimate these sorts of integrals? You always end up you always use the triangle inequality for integrals. That is you push the absolute values inside. So let's push the absolute values inside. Oops, I just made the mistake that I criticize several people for doing. So you push the absolute values inside. Okay. But the problem with that is that the stuff you have there might change. There might have been some cancellation before that is no longer there. And so maybe this gets bigger. Okay, it won't get any smaller, but it might get bigger. So, because it may be, before when you were doing this integral here, there's like some stuff, sometimes this is positive, sometimes it's negative, so that cancels out before you take the absolute value. But now, since you're taking the absolute value first, you're never going to get cancellation. So all you have now, all you can do there is sort of make it bigger. So this is triangle inequality for integration. Okay. So what? So everybody good with that so far? Okay, so it's so as you can see, well, it seems like, so if you look at these two terms, whatever the details of that condition were, this term over here, there's a question. But let me just finish this. This term over here is something you can control, and the f, not so much. And so our next step is going to be to control that h of x of t minus h of 0t term. So if h is not continuous, can you still apply triangle inequality with absolute value? If h, the reason I said that h is continuous is that if h is not continuous, we don't know, we might not be able to integrate it. So I could have just said like h is Riemann integrable. Is Riemann integrable in t for every fixed value of x? That would work too. That wouldn't change the problem at all. So so the continuity of h is just a lazy way for me to say like, oh, you can the integral, you can actually do the integral. Okay, so we're going to control this thing, and so how are we going to control this thing? So, well, it says there's some delta one of epsilon one, and so it looks like we can make that thing. I'm going to do this sort of the hard way. I'm going to sort of say there's going to be an epsilon one there, but I'm not going to say what epsilon one is quite yet. There's going to be an epsilon one. So this is so it might be that whatever this is, it's going to this is going to be. Oops, I'm almost out of time here. Almost out of space here. So this is going to be. We're going to replace that with an epsilon one that's going to be bigger, and then we have the absolute value of f of t here, dt. Which is equal to, now since epsilon one is constant, you can pull it out. The integral of epsilon one times the integral from minus one half to plus one half of the absolute value of f of t dt, which is at most, is it at most or is it equal to? Oh, it's equal to 3. Okay. There we go. That's irritating. Okay, so that's equal to 3 epsilon 1. And now that's the thing that we need to be less than epsilon. Okay? And so that's why we're going to take, let epsilon 1 up here be epsilon over 4. And, you know, I think most people put 3, and yeah, I let that go because that's sort of not worth fussing about. But I personally prefer like 4 there because there's no kill like overkill. Yeah. All right. So if we let epsilon 1 be epsilon over 4, and then we let delta be delta 1 of epsilon 1, which is the same thing as saying delta 1 over epsilon over 4, then at the end, well, epsilon 1 is epsilon over 4. So this is 3 epsilon over 4, which is in fact less than epsilon. Ta-da! Well, it's a smaller smiley face because it doesn't fit as well, but it's happier. Something like that. Okay, so there's the answer to number 7. And yeah, so and note that this of course, as you saw in 131A, this business came last, right? Like, we did all the stuff. We knew that something had to happen here, but we didn't know what. And at the end, the result we got is, well, it's 3 epsilon 1. That's as good as it's going to get. And so epsilon, what is the epsilon 1 that we're going to pick? Well, it's going to be epsilon over 4 works. And so we go back to the beginning and say like, oh, well, the thing we really want to do all along was to pick epsilon 1 equals epsilon over 4. Yes, as long as it makes it less than epsilon, then we're good. It could be epsilon over 5, epsilon over 27, epsilon over 42, whatever. As long as you get something less than epsilon, then we're good. And in fact, really, because of that, it's really true that if you get less than or equal to that works just fine. That's always true because if you could be less than or equal to epsilon, well, you can also be less than or equal to epsilon over 2, which would be less than epsilon. So that works too. So any questions about number 7? Almost done. Okay, I mean, as always, there's when we replace, yes, there's a step when you replace h of xt minus h of 0t with epsilon, can we switch this less than or equal to just less than? Yeah, I have to. Yeah. I think. Well, less than or equal to always works. If you put less than, I think I let it go. That's why I let. That's why I let the. That's why I let the epsilon over 3 folks go because as long as there's a strictly less than somewhere in the middle here. But I think if I were to be really super picky, there are examples of f of t where it could be. Let's see if it's strictly less than everywhere. Sorry, no. Yes, you could replace the less than or equal to with a less than, but I don't know. I just spent like a minute thinking about it, so it doesn't seem worth it. Let's have less than or equal to, and then just overkill later. So the answer is can we switch this particular less than or equal to a less than? Well, you could probably, but I don't know that. I'm the sort of person who has to go back, and I actually just literally did this today. I didn't go back and check to see if the stove was on. I left the house and went back to make sure the door was locked. So if you're like that, then you might as well just use less than or equal to. Yes, it is safe to overkill. I mean, I could see potentially some scenario where you could get some mileage out of it being strictly less than, but yeah, I mean, you have to think about it. At least I would have to think about it. Okay, any other questions about number 7? Yes, there's no kill like overkill. Oh, okay. Yeah, I don't know. There's probably some less than was continued. Oh, yeah, right. So the continuity up here should always be, these should always be less than the end result. You always want to be less than, just because, well, it actually, to be honest, it does end up being logically equivalent. But the less than is better because it sort of fits higher. What is literally the case is that it generalizes better to the definition of continuity that you see in topology. So hey, come take topology, and then you'll see why I'm being so fussed about why everybody got so fussed about this less than instead of less than or equal to. But yeah. Yes, continuity. But the fact is, you can actually a lot of these things end up being logically equivalent to the lesser. The lesser equal twos are logically equivalent, even though it's better not to be. It's better not to fuss with it. You just get the one version down, and that's all that's consistent. Any other questions? I mean, a lot of good points here. Okay, coming in on time and under budget. Okay, right. So A, state the Hilbert space absolute convergence theorem. And this actually, this part is actually one of the things that trip people up quite a bit. Yeah, so let E sub n be the usual basis for L2 of S1 and suppose ANs are complex numbers. Then the HS Act says that the sum over all integers of AN, EN converges if and only if. All right, and it's going to be the sum of something. And now, okay, so here's the hard part. The hard part to remember is that it's the sum. Okay, strictly speaking, though, I'm going to get rid of this in a minute. The sum of the thing to remember is that it's the square. Everything you have to square everything. So it's what the theorem literally says is that the series converges if the if the sum of the squared lengths of those vectors is it also converges. And the thing that got a bunch of people, well, I think actually, well, I don't know a bunch, but a fair number of people, is the square part. Oh, let me do note that I for later that this is equal to 1, and so I'm just going to ignore what comes later. But this is as written out in the red, that's literally what the theorem says. So yeah, so the function series converges in L2, I should say, in the inner product metric, if and only if this series of numbers, and it really is a series, it's a sum of a bunch of squared numbers, basically, also converges, if and only if. And as we'll see, this you need to have the square over here. If you don't have the square, then you actually get stuck at the next part of the problem. So, questions so far? Yeah, that was important enough that worth. And it's a subtle thing going on there that that you really do need the square. Okay, so let's put this sucker to bed, huh? B. Now suppose that this particular thing is true for condition that this bound is true on the absolute value of a sub n, and prove that the sum of the a and e n's converges in the inner product metric to sum f in L2 S1. Yeah, the square. Yes, there's no, well, I don't know what better, but there's no more effective way to remember something like that than getting it wrong on a test. I can still tell you stuff that I got wrong on tests when I was 20. That bugs the heck out of me. But I remember it now. Anyway. Okay. So yeah, it's not that it's learning by trauma. I don't know if it's it's not the nicest way to learn things, but it does work. Okay. Right. So the point is that because we have HSAct in our back pocket, we know that the thing to analyze is that thing squared. So observe that the absolute value of an squared is at most 1 over the sum, 1 over the absolute value of n to the 3/4 plus 5 squared, which is less than or equal to. I'm just going to throw out the 5. I'm going to throw out the 5 because a smaller denominator is a bigger fraction. Smaller denominator means a bigger fraction. So there's really 1 over the absolute value of n to the 6/4, as many of you put it, for n not equal to 0. Okay, so that's the key thing, is that if you compare the squared value of the absolute value of a sub n, then you get this thing over here, and that's now the sum over all non-zero n of 1 over the absolute value of n to the 6/4. That thing converges by p series and now with p, because we magically doubled p, p equals 6/4, which is in fact greater than 1. So that was a little mean of me. That was a little mean. That was a kind of a little curveball, a little bit of spin on the old fastball. That it doesn't work. It doesn't. If you don't remember the square, it doesn't work. And so that thing converges by p series. So because one term, in fact, any finitely many terms, the one term n equals 0 doesn't affect convergence. Comma, the sum over all n integers n of the sum of the absolute value of a sub n squared converges by comparison. Right, which is really the way that you prove that any series. There's like a few examples we know. We know geometric series, and we know P series, and then everything else is really by comparison. It's like estimates compared. That's it. That's really all I know how to. I mean, I know. I guess I know some things that look fancier, but in the end, they're just comparison. Right. Okay, so because one term doesn't affect convergence, that series converges by comparison, and so that which means that by the Hilbert space absolute convergence theorem, the sum over all integers of an en converges in the inner product metric. Okay. That is, yeah. Would I have fussed about I don't think I would have. I suppose I could have. I think I know. I'm pretty sure that in practice I did not. Um, if I were feeling really picky, I guess. No, you would not get any. Okay, you can go get your 1 point back later if I renege on this. But yeah, if you hadn't mentioned the n equals 0, like, well, okay, whatever. It's just one. It is just one term, and so it is. It is in the professional level. Everybody knows like one term doesn't matter, so who cares about one term? So no. Well, I mean, I'm not always the most consistent person. I try, but so I can't really guarantee that that I won't take off points. But I think I feel safe in saying that I should not take off any points if you forget to mention that n equals 0 term. There. I want to make the 6 look a little more prominent. Okay. That's it. That's 5, 6, 7, 8, as promised. Any quick questions or anything I should address before I turn off the recording? And then you can ask more questions after the recording's off. Okay, bye YouTube. Bye recording.